I would like to make to you today is on magic squares, and the reason I want to make this presentation to you is so that I will like to stimulate people to think in this area, and you'll see that it's a fun game. And I will show you a couple of different things, and I will lead you into different places where you can research this concept, and then you can see what I think I have done that's, I believe, fairly new, fairly novel in this area. And I would like you people to help me to find out if it really is. So you look around and see if you find my claims any place else. And then you come to me and you say, Brumnak, forget it. It's all wrong. Okay? Anyway, the idea of a magic square goes back thousands of years, 4,000 years or so. And let me bring you first to the internet, since this is 2008. And on the internet, you can go to Google and you can type in magic squares. And here you will find loads and loads and loads and loads of stuff. Okay? A good place to start is this Wikipedia. And here you see you have basic concepts and somewhat of an outline for you to follow. Okay? And so let's go over here and see what this magic square is and where it started and why I got interested in it and what it is, and let's see if we can get some people excited about this, and then you can continue these investigations. Okay? 4,000 years ago, legend has it, in China, they were doing some sacrifices or something, I don't know exactly what, and the answer to the amount of sacrifice that was expected by the gods, whoever they were, came out of the river, the Lo Shu, and on the back of a tortoise. And a little boy looked at the tortoise and saw this diagram. And he said, 15 is the right number. And they said, well, how'd you do that? Well, you see, he says, that's 1, that's 2, okay? That's 3, that's 4, that's 5, that's 6, okay? And that's 7, that's 8, and that's 9. And every horizontal line, every vertical line, and every crisscross, every main diagonal adds up to 15. So everybody said, wow, says this is magic. Okay? So this is the modern version of this magic square. Okay, it's a 3 by 3 square. In each one of these, you put an integer from 1 through 9. And then every horizontal, every vertical, and every main diagonal adds up to 15. Okay? And you can read about this over here, the Lo Shu square, here it is. You can read about it. You can spend a long time looking at it, and then you can go through how in different cultures this was accepted, Arabia, India. Eventually like everything else, it got to Europe. Okay. Eventually, it got to Europe. And there are many ways of constructing these squares. And I got interested in these squares as a game. You know, I found it interesting, and I looked at this, and I played with it, and I looked at different, and most of these, not all of them, but most of these techniques were very involved, very complicated. And the reason for that, it seemed to me, was that people didn't really examine the square. They had a square, and then they tried to justify why things were so. And if you read the literature, books, articles, internet sites, etc., there are hundreds of these, and you will see that they were used in astrology, they were used in magic, they were used in many different applications. In reality, what can you do with a magic square? The best thing you can do is entertain yourself. It's a game. It's a nice game. The only real application that I have seen, and I don't understand why, because I'm not a musician, is that Indian music, you know, sitar and related sounds like that, follow patterns that are basic to these magic squares. Like I said, there's many different techniques of making these magic squares. In 1514, a gentleman named Albrecht Dürer, this gentleman here, yeah, cool dude, huh? Look at that. Oh, there's no ring in his nose, but he's still okay. This gentleman was a German or Austrian, I forget. Probably at that time was basically the same area. He was a philosopher, a mathematician, a carver, a painter, you name it, he did it well. Okay? And this is one of his paintings. Okay? It's called Melancholia, Melancholy. Okay? And you can see everybody's sad. Okay? Everything is sad. Okay? And they probably just came out of listening to a German opera. That's why everybody's sad. You see. It took too long. Anyway, what he did with magic squares, he dabbled in magic squares, and what he did is he made a 4x4 magic square, which he incorporated into his painting, and very cleverly he made the two middle numbers on the bottom come up with the date that he did the painting, 1514. So that's pretty clever, okay? So whoever does not fall asleep during this presentation may have this poster. Whoever's left awake, we'll give him this poster. Okay. Now, in order to tell you what I tried to do here, I'm going to present to you what I did with magic squares. In other words, I always look for simple things. You see, I'm an electrical engineer. I follow the path of least resistance. Okay? So I like simple things. Why? Well, probably because I don't understand complicated things. But I like simple things. If you can express it simply, you know it. If you start babbling for half an hour, you don't know what you're talking about. Okay? Okay? So simplicity is the key. So let me first impress you a little bit, a little shocking. I need two people. Would you mind coming here? What we have here is okay, come on this side and just, this is I forgot, I can't even think. 101, no, 102, 102 by 102 magic square. Okay, so we have here, and this is small, okay, because we can do bigger. So we have 102 by 102 rows and 102 columns, magic square. It starts with a 1. Some increments are 2, some increments are 4, which I'll explain to you what they mean. Okay, right now I'm trying to get you to say, wow, look at all that. Okay. And the sum of every vertical, every horizontal, and the 2 main diagonals, this one and this one, okay, everything adds up to 1,081,914. Okay. So the sum for this is 1,081,914. Okay? Every vertical, every horizontal, and each main diagonal adds up to this number. So what are these techniques? And I leave it up to you to go on the internet, get the textbooks, go in the library. Yes, there is a library with real books. Okay. It still exists. Yeah. You can sign them out. You can look at them after you dusted them off. And take a look at this, and you can research the background, the history, where they were used, why they were used, etc. What I'm going to present to you today, okay, and I know the secret of a good lecture, which I've been informed seems to work. Okay, a good lecture has a good beginning, a good end, and not too much in between. So we don't want to lose anybody. Okay, thank you very much, gentlemen. Roll it? Okay. Yeah, you can roll it up. If anybody wants to check that those really do add up to that number, you're welcome. Okay? You're welcome to do that. Okay? Now, I will present to you fairly simply the mechanics of these squares, and then I ask you to check out if you can find these methods anyplace else. Okay? So actually, you're working for me. Okay? You thought you get the pizza for nothing, huh? There you go. So, what are magic squares? Well, there's 2 types. There is what is called a pure magic square and a derived magic square. A pure magic square is a square where you begin with the number 1, with the integer 1, and every increment is a 1. So everything is 1. Okay, that's a pure magic square. A derived magic square, you don't have to start with 1. You can start with any number you want. And there's 2 different types of increments involved, as you will see in a few minutes what they are. Okay? Now, there are 3 different configuration of magic squares, you see. The simplest magic square is this one. Okay? That's trivial. There's 1 box, there's 1 number. Everything adds up to that number. I mean, that's trivial. Okay? The next possible magic square is a 3 by 3. Okay? So we have a 1, we have a 3 by 3. Then we have a 4 by 4. And then we have a 5 by 5. Okay, a 6 by 6. And you can go on 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's a 6 by 6. You can have a 7 by 7, an 8 by 8, et cetera, et cetera, et cetera, on to infinity. Okay, this is trivial, so that's not to be considered. However, here we make the following observations. Here's an odd one, you see. 3 by 3, 5 by 5, 7 by 7. Okay? So we have magic squares that are odd. Now this is referred to as the order of the magic square. So that's the order of the magic square. These are odd order. 3 by 3, 5 by 5, 7 by 7, 9 by 9, etc. Okay? But when you look at the even, okay, when you look at the even ones, for example, this one, 1, 2, 3, 4, 4 by 4, 1, 2, 3, 4, 5, 6, 6 by 6. They're both even. However, they're different because, you see, a 4 by 4, an 8 by 8, you notice that the order is divisible both by 2 and by 4. See, 2 goes into 4, 4 goes into 4. 2 goes into 8, okay? 4 goes into 8. However, a 6 by 6 is divisible by 2, but not by 4, okay? Because 2 goes into 6 3 times, okay? But 4 does not go into 6 evenly. So over the years, and this stuff is over 4,000 years old, we have people classified these evens into these two groups, and they gave them names, okay? This one, it's called doubly even, and this one is called singly even. Okay, so a singly even is an even square where the order is divisible by 2 but not by 4. For example, 6, 10, 14, 18, see, every 4, okay? These are not divisible by 4, but they're even, okay? Whereas 4, 8, 12, 16, etc., these are divisible by 2 and by 4. So these are doubly even, these are singly even, and these are odd. So we have 3 types. We have odd, we have doubly even, and we have singly even. Okay? The techniques of generating these different squares are many. Okay? And I encourage you to look in the literature and look at them and find them. Okay, what I was looking for was a very simple way of doing these, simple that even I can do it, okay? Without remembering too much, without doing, et cetera, okay? And the doubly even was already done very simply by Mr. Durer in the 1500s, okay? And I will show you quickly his method, okay, the Durer method. There are other methods of doing this, but the Durer method for doubly even is very simple, okay? You can see that a 1, 2, 3, 4 by 1, 2, 3, 4, there's 16 cells in here. Okay? You can put in the numbers 1 through 16, okay? And then every horizontal, every vertical, and every main diagonal has to add up to the same number. Now, what is this magic sum? And the magic sum is always equal to m cubed plus m over 2. Okay. This was developed over the years by different people. I don't know who exactly. So you see that a 4 by 4, okay, that's one way of doing it. There's another version of this formula, which is m over 2 times m squared plus 1. And you notice it's the same formula, but it's a little easier to use, okay, because, you see, a 4 by 4 would be 16 plus 1 is 17. And this is 4 in front. And 4 divided by 2 is 2, and 17 times 2 is 34. Okay? So this formula here is easier to use than that one. Okay? This holds for all of these, each one of these, okay? As long as they are pure. In other words, you start with a 1 and all the increments are 1. If they're not pure, then there are different things you have to add, and that's where I think I did some innovation, but I'm not so sure because every time I look at it, I see that somebody did it before, okay? And this stuff's been around for 4,000 years, so probably somebody did. Okay? But you can be the judge. So let's see how Mr. Durea did this. Okay? See, right now he's smiling at us. People know who he is. Okay? Mr. Durea said that you start here and you end here, and you make believe that there are 2 main diagonals like this. Upper left to lower right, upper right to lower left. Okay? And those 2 main diagonals. And you start writing down the numbers, 1 through 16 in this case. But you only write them down if they fall on the main diagonal. So you write the number 1. You don't write 2 and 3, but you write the number 4. No 5, okay, but 6 and 7, yes. No 8, no 9, 10, 11, no 12, 13, no 14, no 15. Here is 16. Okay? So you write down the numbers only if they fall on the main diagonals. However, you do keep the count. Okay? Then you reverse the process. You go backwards, and you make believe that your last entry, that's where you place the number 1. But since it's busy, you don't put it in. And you fill in the rest. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And that's Mr. Durea's method. And if you look at this adds up to 34. 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 This adds up to 34, 34, 34, 34. This is 34. And this is 34. Okay? And you can check it out. All the even ones can make, like, you can make it any size you want. Okay? As big as you want. Okay? And as a matter of fact, we have, since this is pretty set, we have Mr. Trowbridge here working on computer simulation of these concepts that we're discussing now. Okay? And soon we'll have generated due to his efforts, excellent programming that will generate this. So we can just tell it, give me a 1,000 by 1,000, and if you have a big enough screen, but then Jerry can tape them together and we'll do fine. Okay? So no need for this. This is simple enough. Agreed? Doesn't need any massaging. Even I understand it. Okay? That's pretty good. Okay? Now, the odd. There are many ways of doing art. Many ways. There's, you just look at it, people say, I see it. I don't know. You know, I can look at it until the cows come home. I don't see it. Okay? I need to be hit on the head a little bit. You know, need something a little more concrete. And there's something called the, I don't know, if you play chess, you'll recognize the knight's move. You know, how a knight moves in chess. There are different ways of, et cetera, et cetera. And people that were involved in these kind of development of these techniques are, well, it goes back to the Persians, the Indians. Eventually, the stuff worked its way through like Constantinople. It came into the West. And it wasn't until later on that the West got introduced to this. And probably, and I hope these guys don't come and torment me, but probably the names associated with some of these methods that we know in the West were probably copied from much older methods that were used in Persia, Iran, and in India and stuff like that. But anyway, I said that. I said, man, all this stuff is so complicated. I really don't see, you know, don't see how to do it. So let's see if there's an easier way. And I found a technique that I called the gamma plus 2. In the Greek alphabet, this is uppercase gamma. Okay? And the reason I called it the gamma plus 2 is because this is the motion that you go through to fill in the square. Okay? And an odd square always has a middle subsquare. You see? Always has a middle. So you always start just to the right of the middle. So here we put the number 1. Okay? And one thing that I realized, I thought it was unique, and then I found out that it wasn't because I saw it some other place, is that what this is, you see, this is a two-dimensional representation of the skin of a donut. Because you see, a donut looks like this, you see. So if you cut it, this meets that. And also a donut comes around, so this side meets this side. So when you flatten this out, if you run out of space on the right, you're really on the left. You continue on the left. And if you run out of space going up, you continue on the bottom, because you see the bottom and the top touch, and the left side and the right side touch. Think of a donut. Okay? So keeping that in mind, okay, we look at this, and my technique is this. It's up and over. That's why that word gamma. By the way, originally I made a mistake, like nothing unusual for you, right? And I was corrected by Professor Metaxas, who says, Brumnak says, that's not a lambda, that's a gamma. Being Greek, he should know, okay? So that's a gamma, okay? And by the way, Mr. Metaxas is also working on computerizing some of this stuff. So what's that mean, gamma? Well, you see, is up and over. But over brings you here, you see, because this side touches this side. So you put the number 2 here. Now, up brings you here, and over brings you here. So you put the next number here. Now, up and over is busy. So when you encounter a cell that is already occupied, you go back one step, and you go +2 to the right, +1, +2, which is really here. And then you go up and over, up and over. Up is here, over is here, it's busy, so you go 2 to the right. 1, which is here, 2 here. Up is here, over is here. Up and over is here. And everything adds up to what? Well, let's take a look. M is 3, m squared is 9, plus 1 is 10, divided by 2, this is 10. 10 divided by 2 is 5. 5 times 3 is 15. Everything adds up to 15. And there, 9, 15, 10, 15, 9, 15, 11, 15, 10, 15, 11, 15, 6, 10, 15, 8, 10, 15. Pure magic square. Okay? Pure. Okay? Starts with a 1. All the increments are 1. Okay? Let's do a little bigger one just to give you the feel for it. We're going to do a 5 by 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, where's the middle cell? This is what? 1, 2, 3, 4, 5. Well, you know, there's 2 types of mathematicians in the world. There's 3 types, the ones that can count and the ones that can't. All right. Okay, that's a 5 by 5. Now we can find the center. Here it is. All right. So here's the technique. You ready? 1, 2, up and over 3. Up is here, over here 4. Up and over 5. Busy. 6, up and over 7, up and over 8, up and over 9, up and over 10. Busy. 11, 12, 13, 14, 15. Up and over is busy. 2 to the right, 16, up and over 17, up and over 18, up and over 19, up and over 20. Up and over is busy, 2 to the right, 21, up and over 22, up and over 23, up and over 24, up and over 25. And this is going to add up to what? Well, let's take a look. It's 5. 25 plus 1 divided by 2. This is 26. 26 divided by 2 is 13. 13, this is 65. Everything is equal to 65. Guaranteed. Okay? You can check it out. So I said, wow, look at this. The gamma plus 2 method invented by Brumnak. I said, this is going to be cool. Except after further investigation, I found out that people did this 2,000 years ago in Iran. Okay? Yeah, well. But it's okay because, you see, by the time it got to the Western world, okay, this was there. But then what I did is I developed 7 other variations of this method. Okay? There were 7 other variations, and 2 of them I found in the literature. This was one of them because as you could start here, so this is, here's the center, and you could start here, up and over, or you could start here, you could go down and over. You could start here, you go down and over, down and over. You can start here, you can go up and over, down and over. And you can start here, you can go up and over and down and over like that. So I saw these other 7 methods, so there's 8 altogether. And so far in the literature, I have only seen this one and this one described. So my number 1 and my number 8. Okay, the other 6, I haven't seen anywhere. So I want to enlist your help. You look around if you're interested, see this. See if you see anything else than these 2, okay? And let me know. Okay, I haven't been able to find them. Now, so now we have a simple method of doing the odd, okay? Mr. Durea's method of doing the even, no problem. A simple method of doing the odd is like this. The toughie, the really tough one, is the doubly even, okay? No, the singly even, right? This is, yeah, the singly even. This is the doubly even here. Durea did the doubly even. Okay. Okay, he did the doubly even. The singly even is really tough. It doesn't conform to any of these techniques. Okay. However, a gentleman in 1918, and his name was, what the heck was his name? I forget. Strackman, I think, or something like that. Okay, let me check here. Okay, anyway, it doesn't matter. I'm not going to. You can look it up. In 1918, this gentleman came out with the following technique. Now, I have a suspicion. I mean, this guy was an ambassador, was an English ambassador to Iran, Persia. Okay, and he came back with this technique. So I don't know him personally, and we can't ask him anymore. So. Okay. So I don't know whether he saw this and brought it back, and nobody knows if I don't know if he really took credit for it or just said it. But anyway, here is what he did. He said that any singly even one, for example, a 6 by 6, you see, a 6 by 6, could be broken down into 4 3 by 3s, you see. Okay, I have it already drawn here. Here's a 6, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. And what he said is this. You see, if you break this down this way and this way, you see there's 4 3 by 3s. So the singly even, it becomes 4 odds of half the size. Okay. And he named them like this, and he said you have to do them in this order. Okay, A, B, C, and D. And if you do them in this order, you do the A first, then you continue with the B, then you continue with the C, then you continue with the D, and I'll demonstrate to you what I'm talking about. Okay. Then all the vertical sums are the magic sum. However, the horizontal sums are not. And the 2 main diagonals are not. However, if you interchange some of the cells between the bottom and the top, keeping them in the same column so as not to change the perfect sum coming down, you will wind up with a magic square. And his conclusion was, well, unfortunately, there is no method of doing this. Each one is an individual. Well, I think I found a method. And the reason I was able to see the pattern is because of Excel. Okay? And the guy in 1918 didn't have Excel. Okay? So he had to add up all the stuff by hand. Well, in Excel you can add this, so I did a few of different sizes, and I saw a pattern. And I believe it's original. Okay? Now you guys go out and look, and you tell me if it is or if it isn't. Okay? So let's see how it's done, and then I'll show you my pattern. Okay? So what we do here is, you see this one here, you start with A. So we'll only discuss pure ones. These are a little more, take a little longer. And by that time, between having eaten the pizza and listening to all this hot air here, okay, we don't want to make you too comfortable. Okay? So here we go. So here's the middle, right? So 1, up and over 2, up and over 3, busy, 4, 5, 6, up and over busy, so 7, 8, and 9. Okay, here's square A. You repeat this starting with 10. See the next number here, and it's the same pattern. 10, 11, 12, right? 13, 14, 15, 16, 17, 18. Okay? 19, 20, 21. Okay? Busy, 22, 23, 24, 25, 26, 27. Okay? 28, 29, 30, 31, 32, 33, 34, 35, and 36. Okay? That's the square. Now, what magic sum do we expect? And how do we do that? Well, it's m squared plus 1 divided by 2. Okay? M is 1, 2, 3, 4, 5, 6. Okay, so this is 6. 36 plus 1 over 2. 6 divided by 2 is 3. 36 plus 1 is 37. So here is 7 times 3 is 21. Carry 2. 3 times 3. So we're looking for 111. That's the magic sum. And indeed, if you add this up, you'll see that it's what? It's 111, 111. Everything is 111 this way. However, it's not 111 horizontally, and it's not 111 on the two main diagonals. So how do you make this magic? Okay. Oh, the guy's name was Strachey. I knew. So eventually, Mr. Strachey. Okay. So he said that you have to change, you have to move some stuff around. Obviously, you have to move it in the same column so as not to upset the already perfect sums. So what you do here is you interchange the 2 and the 29. Okay? You interchange the 2 and the 29. You see? You interchange the 4 and the 31. Okay. And then you interchange the 5 and the 32. And if you do that, these will be 111, and these will be 111 also. Okay? All right? if you're taking ET, where do we do Excel? It's a good exercise for you, okay? Set this up in Excel, put in the numbers, and copy and paste and move them around, and you'll see that everything works out fine. Okay, now, what I think I found out here is that, well, he said that, see, you have to make these changes and there's no pattern. But I found a pattern. And here it is, okay? And you are my scouts. You go out and see if you can find this anywhere, okay? Okay, a 6 by 6, okay, what you do here, okay, what you do here is you move everything except the middle, you see. And then you just move the middle. And nothing on that side, okay? So for a 6 by 6, the number of columns to be moved are 2 and 0 over there. 2 and nothing. Okay? And you notice that the leftmost column, you exchange everything except the middle one. And then the last column, you only exchange the middle cell. Okay? Now, what's the next singly even number? What's the next one? 6, 10. So for a 10 by 10, okay, here you're going to move 3 columns, and here you're going to move 1 column. Okay? You're going to exchange that. And the way you do it is the first column, you exchange everything except the middle. Okay? So 10 by 10 would be what? What's 10 by 10? 4, 5 by 5, right? So you would have these 2 and these 2, right? These 2 get exchanged. Then these 2 and these 2 get exchanged, but not the middle one, okay? The next one, you exchange this whole thing with this whole thing. And the next one, you just exchange the middle, okay? So you see there's 1, 2, 3 involved. And over here, all the way over, you exchange the whole thing. You exchange this with that. Perfect magic square. What's the next one? A 14 by 14, you see, it's the first 4 columns here and the last 2 columns at the end. The last 2 columns, you exchange this one with this one, and this one with this one. And the first 4, everything except the middle, okay, so that gets exchanged with that. This gets exchanged with this. That's 1. 2, the whole thing. 3, the whole thing. But 4, only the middle. Okay? So you see the pattern here. This is the pattern, you see. that gets exchanged with that. And here, this is always in the home. And the numbers go like this. Okay? The numbers go, starts with a 6, 2 and nothing, 3 and 1, 4 and 2, 5 and 3, 6 and 4, okay, etc. Okay? 7 and 5, 8 and 10. And so far, okay, we have shown you a 102 by 102. You see, 102 by 102 is 451 by 51, you see, done by this method. Okay? And they work. Now, for 102, okay, we would have to write all the numbers and figure out how many we got to swap. Okay? And so how many would it be? Well, 18 is 5. Okay. What's the next one? 22, 6. What's the next one? 26, 7, and so on. Eventually you'll get to 102. Okay? And you'll see how many you have to swap. But that's the technique. Okay? And we have a couple of people working on this so they can we can make this automatic, because, I mean, after a while, you know, it's fun and stuff, but who wants to stay there and do this manually, okay? And if you take Dr. Nashelsky's computer course, that's probably your next homework assignment. Is that correct? Mm-hmm. Absolutely, okay? So anyway, that's the idea. Now let me just show you, let's see, how I would do this. And again, I encourage you to look at all these things, and they have all sorts of places where you can look. All you ever wanted to know about magic squares, well, you know more. Okay? Magicians use these. They use tricks, magic totals, see 4x4 magic. Well, now you know more than most of these websites. Okay, there's a birthday magic square, for example. See this gentleman here, Mr. Farrar, who's a magician in England. Okay, says, let's see, what day of the month were you born? The 11th? So the 11th, so you write a 2, right? Very good. What month were you born? 5? Okay, and what year? 18, it's contagious, you see that? 1986, okay? You see, he listened to me long enough now, he's totally confused. Eh? Right here? Whoa, look at that. So here is the 11, okay? And this is what? 1986, okay? Calculate, here you go. Here is your magic square, okay? Magic square has a total of 121. Every vertical, every horizontal, and every main diagonal is 121. And so you have all these little games you can find, okay, on the internet as usual, okay, for free. Check it out. You don't even have to steal it. Okay? So where's the fun? All right, so anyway, you can go there. You can go to very sophisticated formulas that you may or may not want to look into. But that's why I sat down and I tried to figure out methods that I'm at ease with, that are very simple. And you can see that Mr. Durer did a quite simple one for the evens. okay, for the doubly evens. Okay, this one here is a nice one for the odds, and you can use that one again with Mr. Strachey's help and breaking it down into this format, and using my switching methods to get the singly evens. Okay? So very nice little methods. Okay, so let me just show you. What I would do here, let's see, we're looking for Microsoft Office, and we're looking for Excel, okay? Looking for Excel. Okay, so now we're going to do and I'll show you how it's easy to use. Okay, we're going to do a 5 by 5, like so. In order to see what we're doing, I mean, since this is the IEEE club, right, and stuff has to be electrically oriented and computer oriented, well, here is the computer application of magic squares, okay? So we will go here, we will format this, and we will format let's see, the cells, and we want borders, and we want the crisscross and all around. So this way we see where we are. Okay, now these are a little big, so we'll make them look like squares, like so. Okay, and here is the middle one. Here's the middle, so I'm going to start here. Okay, so this is 1, 2, 3, 4, 5. You see, up and over. Up and over is busy, so you go back and you go +2, 6, up and over 7, 8, 9. Up is down, over is here. So this is 10. Busy, so you go 2 to the right, 11, 12, 13, 14, 15. Up and over is busy, so you come here, that's 16, 17, 18, 19, up and over 20. Up and over is busy, so you go here, 21 +2, up and over, 22, up and over is here, 23, up and over is here, 24, up and over is here, 25, okay? Here we want a sum, okay, 65. Copy the sum all the way down, 65. Here we want a sum, 65, copy it over, 65. Here we want a sum, but we want this sum. We want this plus this plus this plus this plus this, and that's 65. And here we want a sum, but we want this one, so it's this plus this plus this plus this plus this, and that's 65. Voila. Magic square. Okay? So I hope I didn't bore you too much, and thank you for coming. I hope you enjoyed the pizza, and I'll see you when I get my glasses.